Thank you for that introduction, and thank you for everyone for taking the time to be here. And thank you to the symposium organizers, including Marcus and Lauren, for their help over the last few weeks. The phenomenon that I'm going to talk about today goes by many names. It's often called the 536 mystery cloud. Sometimes it's referred to as the 6th century year without a summer. As I will stress, it is best understood as a decade or so long sequence of pronouncedly cool summer seasons. I refer to it as the 536-550 climate downturn. Much has been written recently about late antiques changing climate, so it might help to position clearly some of the phenomenon paleoclimatologists, archaeologists, and historians have been discussing. Broadly speaking, we should very much hesitate, of course, to speak with broad strokes when talking about long past climates, but broadly speaking, late antiquity saw an extended period of cooling spanning, according to what Climate Proxy 1 reads, the 4th or 5th century to the 7th or 8th. Within that extended period of cooling, which is sometimes curiously identified as the Vandal minimum or the Dark Age cold period, there sits a pronounced period of cooling identified only in 2016 and coined the late antique little ice age, or the Laulia or Laulia. The Laulia, as defined in 2016, began in 536 and petered out in the 660s. Within the Laulia, at its outset, we find the 536-550 climate downturn, the most pronounced stretch of summer cooling of late antiquity and of the Laulia, therefore. So we can imagine these three overarching climate trends nested together: the extended period of late antique cooling, the Laulia within it, and then the 536-550 climate downturn at the onset of the Laulia. This scheme, for me, makes these phenomena digestible. At the same time, however, we need to stress, as colleagues in the paleoclimate sciences do, that speaking of climate in these broad strokes greatly oversimplifies things, and it pushes under the rug a great number of uncertainties and a great number of unknowns. To speak of these climate phenomena as I just have risks, in my opinion, misleading non-specialists and possibly facilitating the construction of erroneous histories of climate and society. I hope in demonstrating this, I hope to demonstrate this by looking specifically at the 536-550 downturn in some detail. I stress in what follows that the significance of this event as it relates to climate, not necessarily as it relates to historical ecologies or societies, is pronounced. Climatically speaking, the downturn is not a Byzantine or a late antique phenomenon. It is in some ways northern hemispheric, and in other ways it is actually global. All the while, however, we must conceive of it as being very much local, intensely local, as people experienced it on local scales. I also stress that paleoclimate sciences are fast moving, much, much faster than archaeology or history, and that to write late antique climate histories, one should work towards becoming conversant in the paleoclimate sciences and really consider interdisciplinary collaboration. Becoming conversant in the paleoclimate sciences and really considering working in interdisciplinary teams. It is essential, of course, to remain current, and it is also essential to treat the paleoclimate sources with the same care that one treats their historical sources. Over the last 20 years, climate change beginning in 536 has caught a good deal of attention in scholarly and in popular circles. The vast majority of academics who have mentioned 536 cooling have naturally stressed its significance. Mid-6th century climate change has featured prominently in histories of Byzantium and far beyond it. From Eurasian steppe empires to the so-called Maya hiatus, to late Iron Age Scandinavia, to the history of irrigation works in Southeast Asia, scholars have assigned a very prominent role to cooling beginning in 536. Most attempts to link up 536 cooling with societal changes are not, I would say, not monocausal, but they do tend to be reductionist and to assume often causation and correlation. At the same time, historians less interested in or less concerned with the natural world and the paleoenvironmental sciences have tended to dismiss 536 as overblown and insignificant, almost as a facade of a climate disaster. On the basis of what we know now in 2021, the most recent article came out only last week, in fact, that reflects on this, I would argue that both stances lack robust support. The 536 downturn was neither an insignificant local dimming nor a disaster triggering global blackout. Recently, mid-6th century climate change has come into focus, but on the basis of what was known 20 years ago, when arguments for and against the significance of 536 were first common, there is no doubting that the naysayers were then in the right, and that theories about 536 climate crises, whether in the Yucatan, Mediterranean, or the Central Steppe, were poorly supported. Now in 2021, however, it is vital to recognize that mid-6th century climate change has moved on, and that 536 is not today what it was 20 years ago. For instance, the science in Arjava's then thorough and convincing 2005 Mystery Cloud article was already out of date by 2008. The scientific context in which we must interpret the written evidence has changed greatly, and it changes almost on a yearly basis. Antiquarians in the 18th and 19th centuries drew attention to textual evidence that would eventually lead to the discovery of the mid-6th century downturn. Yet climate change commencing in 536 was, I would argue, initially discovered only in the 1980s. In several publications of that decade, Richard Stuthers, an atmospheric scientist at NASA with a classics degree, connected a handful of 6th century eyewitness accounts of something unusual in the sky with a then new Greenland ice core record spanning the late Holocene of large volcanic eruptions. By 1988, passages in the writings of Procopius, Cassiodorus, John of Ephesus, John the Lydian, and Pseudo-Zachariah Rector were all considered fundamental to the reconstruction of a mid-6th century climate event. That's by 1988. The many months of mystery clouding or sun dimming or dry fogging those authors reported over the Eastern and Central Mediterranean in or around 536 were connected by Stuthers to a large eruption archived in the early ice core record of volcanic sulfates from southern Greenland and dated to within 10 years of 540. By 1985, another independent Greenland ice core had emerged, the Dai 3 core, and it seemed to identify a large eruption about 535. There was growing evidence, therefore, for something big happening in the 530s. Stuthers suggested that Rubal volcano in Papua New Guinea as the source. That eruption at the time was estimated to have erupted within a century of the year 700 CE. Now, understanding of volcanic climate forcing, the impacts of eruptions on climate has evolved steadily since Stuthers' time, but the basics still hold. Large and violent volcanic eruptions can inject tens of millions of tons of ash, hydrochloric acid, and sulfur dioxide into the atmosphere. The ash and acid fall to Earth in hours or weeks, but the sulfur dioxide, if it enters the stratosphere, can mix with water to produce fine sulfuric acid aerosols. If these aerosols reach the stratosphere, they can dim incoming sunlight on regional, continental, and hemispheric scales, potentially for multiple years. In the stratosphere, these aerosols do many things. Importantly, they absorb and backscatter solar radiation, which decreases the transparency of the atmosphere, warms the stratosphere, and cools the Earth's surface. Recent eruptions, like that of Pinatubo in the Philippines in 1991, which you can see on the slide, were far less explosive than the eruptions of the mid-6th century. Yet 20th century events like Pinatubo were observed instrumentally to have lowered mean global temperatures by 0.1 to 0.4 degrees Celsius for upwards of 3 years. And more dramatic cooling happened in the first 3 months and where the veiling was densest. The the 1815 Tambora eruption, the largest eruption on the planet of the last 250 years, but still smaller in some proxies than the mid-6th century eruptions, is now thought to have caused a temperature drop of upwards of 4 degrees Celsius in regions of Europe and North America. Okay, taking a step back for a moment. Ice layers can archive sulfate and tephra from large or local volcanic eruptions, which are snowed out in the best cases over the poles, where ice is generally well settled and accumulates annually. Good, reliable records of past significant volcanism can be constructed. So ice sheets in Greenland and Antarctica are best, not glaciers, which are more dynamic. Here you can see a volcanic sulfate horizon in a long Antarctic ice core dating to about 21,000 years before present. As Arjava noted in 2005, historians did not pick up on Stuther's pairing of early ice core evidence for volcanism with late antique Mediterranean texts for more than a decade. So there was an ongoing debate in the 80s and into the 90s that occurred only in the natural sciences and hadn't really spilled over into the work of historians until the mid-1990s. Stuther's account of the event, though, did not last. It did have, and I guess it's important to point out, a few shortcomings. There was, for instance, no actual evidence for the effects of climate on any mid-6th century eruption in the 1980s. The volcanic eruption archived in polar ice was then presumed to have caused not only the clouding observed by Mediterranean region authors, but also to have caused considerable cooling. We know now that not all large eruptions, for a number of reasons, affect climate, as the massive eruption of Qianbaishan in 945 did not. It has a VEI, or volcanic explosivity index, of 7, and that's a scale that only goes to 8, and yet it did not have an impact on climate. So not all large eruptions will have a significant impact on climate. More concerning, individual eruption chronologies established for various global volcanoes are hardly set in stone, and yet early attempts to date volcanic sulfates archived in ice cores were repeatedly reworked. Depending on the amount of snowfall a region selected for coring receives, one might layer count back a couple centuries or maybe more, but the ice is often so compressed by the time one is back to the first millennium that other, less secure means of dating are required. The two published sulfate records Stuther's drew on were both redated in the mid-1980s. His big eruption, which he identified or placed at 536, was ultimately pushed back to around 516. And volcanic acid layers subsequently emerged in other ice cores, but they were also, it seemed, too early to be associated or tied to any sort of event at 536. Making things worse, a segment of an international coring effort in the 1990s, the so-called Gisp II Ice Core, was lost. Now, exactly what section was lost depends on who you ask and the dating that they've applied to the core, but quotes in published articles range from either AD 620 to AD 545 or to 606 to 532. In any case, the event that is the stretch of the core that was thought to have potentially contained a sulfate record that would tie up with 536 was melted accidentally after retrieval. In sum, for about 20 years from the mid-1980s, there was no firm ice core evidence for an eruption in the mid-530s. In this non-volcanic interlude, two things happened. Two important things. Many things happened, but two important things happened. Firstly, alternative explanations were raised that proved, I think, too far-fetched for many in the humanities to stomach, making historians in particular less likely to include this event in their writing. Some in the paleo community argued a, quote, medium-sized asteroid struck one of the world's oceans. Different scholars wagered a comet disintegrated in the upper atmosphere that ignited, quote, one or more large-scale forest fires that caused the clouding reported in Mediterranean texts. In 2004, it was even mathematically determined that a comet of less than 1 kilometer in diameter could generate multiple successive years of veiling, and it was suggested, based on some radiocarbon dating of the formation of the Gulf of Carpentaria, which you can see here on your slide, that an impactor 640 meters in diameter landed in Northern Australia, causing the 536 event. All of this was hard to perhaps stomach for many of us in the humanities. The other crucial development, however, in this non-volcanic interlude was the introduction of dendroclimatology. The alternative explanations for 536 that I have just mentioned were driven not by a desire to explain the clouding, though the clouding did receive a lot of attraction in scientific articles, but instead it was driven by a desire to explain, sorry, my family has now decided to blast some music in the next room. It was instead explained by a desire to explain a new climate signal visible in then new tree-based climate proxies. 14 temperature-sensitive tree ring-based proxies for the pre-instrumental period extending back at least to late antiquity now exist. In 1992, when there was no evidence for a volcanic eruption, dendro data was leveraged to reveal a dramatic climate event in the mid-6th century. Suddenly, there was evidence for climate cooling in the 530s. And there was no doubting it. As dendroclimatologists say, trees don't lie. Using long-running dendro sequences, one can fix a reliable, high-resolution annual date to tree signals. The dramatic 6th century climate events seen in trees started precisely in 536, the very same year atmospheric clouding is observed in Mediterranean texts. In 1994, exceptionally poor growth was identified in long-running dendro series from Ireland, the Alps, and Scandinavia. Now in 2021, 536 has been identified as among the 10 coldest summers of the last 2,500 years in more than 35, by my count, dendroclimatological publications. In many of these studies, multiple summers, however, between 536 and 550 rank among the coolest of the Common Era. Indeed, I think the significant development in the intervolcanic or in the non-volcanic interlude was that while Mediterranean texts speak of an atmospheric event of 12 or 18 months in duration, the trees tell us the downturn of 536 was much longer. This was no short anomaly, but a climate downturn lasting more than 10 years. Now, in dendroclimatological series that run 1,500 years, and in dendroclimatological series that run 7,500 years, the decade of 536-545 stands out sharply. 536-545 or 536-550 was not a period of consistent poor growth, however, but in most series, it stands out as one of, or as the coldest sequence of coldest sequence of growing seasons or summer seasons of the Common Era. Of the 10 coldest summers of the entire first millennium CE, in one composite series of six long-running dendro series, 6 of those 10 summers fall between 535 and 540. Most chronologies estimate cooling between 1.5 degrees Celsius and 4 degrees Celsius for several summers between 536 and 550. I mentioned that eruption chronologies of individual volcanoes are not set. Geologists have long used a number of techniques to date large volcanic events. Different methods, of course, can provide different estimates for the same site, and methods have evolved considerably in recent decades. The highest resolution dates for eruptions are dendro-based. Trees killed in an eruption can be excavated and cut or cored and cross-dated with existing dendrochronologies available for the region. An example: 20 years ago, flooding in Iceland exposed a number of trees buried for centuries. About 5 years ago, those trees were shown to have died simultaneously in an eruption, which the trees dated to 822. Geochemical analysis of volcanic tephra dated to the early 9th century and trapped in the Nîmes Greenland ice core tied the eruption identified the eruption as Iceland's Katla volcanic complex. And so the Katla eruption was finally dated to 822. Now, such care has been given to very few eruptions. In some cases, it cannot be given. For example, tephra, like that seen on the slide from the Grip II core, might not show up in a sulfate layer. It might not be archived in polar ice, that is to say. And in the tropics, most trees do not put on clear annual rings, complicating attempts to dendrodate eruptions that occur in the tropics. In 2008, a recalibration of the dating of first millennium sections of bipolar ice cores, so ice cores from Greenland and from Antarctica, identified not one, but two eruptions in the 530s, or very close to the 530s. Only months later, the chronology was independently tested and fine-tuned. It is held ever since August 2008. Very large eruptions occurred in 535 or 536, and in 539/540. There is no doubt. And a smaller event dates to about 547. The geochemistry of tephra archived in a single Greenland ice core identifies one or more eruptions in North America as candidates for 536. A combination of diverse evidence did suggest until 6 months ago, Iliopango in El Salvador was the prime candidate for 540, though there is now serious reason to doubt that. The publications are there on the slide. Stuther's suggestion of Rubal in Papua New Guinea for 536 is long gone, as we now know the 536 eruption was northern hemispheric. In any case, the Rubal eruption has been redated thrice since Stuther's wrote, and it is now securely dated to between 667 and 669. There has been much speculation, a revolving door of volcanoes, if you like. A variety of eruption sites from Alaska to Indonesia to Iceland to Mexico have been held responsible. Whether this uncertainty as to the cause of the 536 event, particularly in the non-volcanic interlude, caused archaeologists and historians to doubt the significance of mid-6th century climate change, I am not certain, but there is now no doubting the significance of these eruptions of 536 and 540 for climate. A figure climate historians know well from Siegel 2015 visualizes on the bottom large volcanic eruptions discernible in synchronized polar ice cores, bipolar ice cores. And on the top, northern hemispheric tree growth deviations from 5 long-running series, which also, because of the location of these trees at high altitude or latitude, also reflect summer temperatures. Some of the data here have been updated. The event at 44 BCE, for instance, is now understood, thanks to a publication only last year, to have been northern hemispheric and not tropical. Here, the red lines identify tropical eruptions and the blue lines northern hemispheric eruptions. But Siegel's 2015 paper remains absolutely fundamental in the history of volcanic climate forcing. The 40 coolest years, or summers, I should say, in these composites are identified on the top, and the 40 largest volcanic eruptions are identified on the bottom. You can see a clustering of cool summers and large volcanic events around 536 and 550, or between 536 and 550. A clustering not apparent earlier in these data and not apparent after for nearly 1,000 years. One scholar recently remarked that they had firsthand witnessed an eruption of Stromboli in the late 20th century. And based on that experience, suggested that other scholars who had put too much emphasis on the 536 and 540 events. Eruptions at Stromboli over the last century plus have been extremely insignificant. They have had no effect on climate. We have to treat the paleoclimatology carefully. Here you can see a visualization of modeling of stratospheric veiling using that same bipolar ice core record or synchronization. This stretches all the way back to 500 BCE and goes right up to the 20th century. Put simply, the more sizable the lava-like mark or blotch, the more significant the volcanic veiling of the eruption, and the more significant in most cases the cooling. Little activity has thus been detected in the 1st, 4th, or 5th centuries, which you can see here. But the 6th century is entirely a different story. Also consider the 20th century and much of the 19th century. It has been 206 years since a cluster of large volcanic eruptions comparable to that of the 6th century has occurred. And the last major eruption of Stromboli occurred in 1921, and its plume, as you can see on this figure, did not reach the stratosphere. There is no sign of it in ice at the poles, and it did not alter climate. You might expect me to say, based on what I've said so far, that 536 event was a disaster of immense proportions. But no, I don't think one can claim that yet. Climactically, it was clearly significant. Whether it was significant generally for human populations at the time, though, is far less clear. Establishing the extent and severity of any particular climate variability is essential, of course, before one attempts to determine the societal effects of that variability. Before one employs the downturn, or the Lollia for that matter, to explain some historical process or event, or to carefully integrate it into their region's history, they must attempt to discern whether it had been demonstrated or has been demonstrated for the region of their concern. In other words, we cannot assume the downturn or the Lollia. Neither can be assumed to have occurred in our region of study. It helps to recall how we define the 536-550 downturn. Defining it also forces us to recall what we do not yet know. The 536-550 downturn, like the Lollia, is defined by summer temperature and summer temperature alone. It is a phenomenon defined by summer temperatures visible in some, but not all regions for which there is available high-resolution paleoclimatology. Temperature is homogeneous over large areas, as was noted yesterday, but available data already indicate that the downturn, or that downturn cooling, was not equally dramatic everywhere, and that it was not of the same duration everywhere. This limited definition of the downturn, focusing on summer temperatures, also reminds us that there's much that we do not know, as there's much more to climate than summer temperature. Other data illuminating latent climate variability in various regions are very much available, but these climate changes, are they connected to the downturn or the Lollia? Or are they something altogether else? I would argue the latter. For example, 2 independent speleothem-based proxies for winter temperatures in parts of Central and Western Europe suggest winter warming during late antiquity, in the same region where dendroclimatology demonstrates summer cooling. In some parts of Europe, then, there appears to have been far less pronounced seasonality in late antiquity. What is the significance of that? We have to look into it. High-resolution precipitation-sensitive dendroclimatology from transalpine Central Europe also demonstrates an extended period of warm season drying in the 5th and 6th centuries, and that was confirmed in the paper published only last week. And that period in the 5th and 6th centuries, of course, overlaps with the downturn and with the Lollia, but is causally disconnected from it. Though the tree ring width based proxy of the Old World Drought Atlas seen at the bottom of this slide does suggest a sequence of pronouncedly arid growing seasons north of the Alps, conditions corresponding to the downturn, but not necessarily causally connected to it. Precipitation is highly heterogeneous over time and space, as Adam has already stressed, but large, low-lying tropical eruptions, like that of 540, have been argued to reduce precipitation levels in many parts of the world. And yet specific linkages between the eruptions of 536 and 540 have not been made. Between those eruptions and drought conditions in Europe and parts of the Mediterranean have not been made, that is. Similarly, wetter conditions in parts of the late antique central and eastern Mediterranean, which are visible in lower resolution paleoclimate proxies, have not been connected with the downturn or the Lollia, and presently stand in parallel to them. Low resolution proxies struggle, of course, to capture severe and abrupt climate changes, but as of yet, there is no reason to associate the downturn with the extended wet conditions discernible in parts of the Mediterranean discussed by my colleagues. And of course, high resolution proxy data as well illuminates extremes in late antiquity in the 6th century that pre and post date the downturn. A high-resolution speleothem-based proxy, precipitation proxy, or hydroclimate proxy, for instance, has identified the most significant drought conditions in the Common Era in southern Arabia in the 6th century, but predating 536 by decades. In sum, for sake of time, the downturn was much more than a mystery cloud. It was neither a local Deming experienced in parts of the Mediterranean, nor a global blackout. Where it can be seen, it was often extreme and long unprecedented. But importantly, the downturn is not all we need to know about late NT climate. It has been the focus of discussions of late NT climate because we can, at least in some regions, see it and date it clearly. That we can see it and date it clearly does not mean it is the climate event we need to, or climate variable or climate phenomenon that we need to be thinking about most. By definition, it is a summer temperature phenomenon. But in most regions like the Mediterranean, where the downturn remains poorly, if at all visible, I would stress, other variables like winter precipitation were far more significant.
Sorry, but we're really out of time.
Okay, yes. I will just say thank you for your attention.
Thank you. Thank you.